Imagine trying to cool down the heat of like 2,500 incandescent light bulbs.
Oh, wow. Yeah.
And we're talking the old school 100-watt kind, right? The
Man.
ones that literally burn your hand the second you touch them.
Right. Those generate an unbelievable amount of heat.
Exactly. So take all 2,500 of those scorching bulbs and just pack them tightly into a physical space no bigger than, say, your kitchen refrigerator.
That would just, I mean, the heat inside that box would be completely apocalyptic.
It really would. But here's the kicker. If your cooling system fails for even like 10 seconds, millions of dollars of silicon inside that box will literally melt.
Melt into a puddle.
Yeah.
It is a terrifying level of thermal density.
It is.
And it's the daily baseline reality for the engineers who are trying to build the next generation of artificial intelligence.
Which is just wild to think about.
It is, because we have moved so far beyond like the laptop or the standard server rack in a closet.
Right, way beyond that.
We're talking about capturing the energy footprint of a small neighborhood and then focusing it into a single 7-foot-tall metal pillar just to teach a machine how to think.
So, welcome to the deep dive.
Glad to be here.
Because whether you are an IT professional who is, actively trying to figure out how to scale your company's data center without blowing the local power grid,
Which is a real concern, yeah.
or you are just someone insanely curious about where the mysterious invisible cloud actually lives and breathes, we're just so glad you're here.
Absolutely.
Because today, our mission is to decode the hyperdense, incredibly complex physical blueprints that power today's enterprise AI and high-performance computing worlds. We are basically dissecting the ultimate computing powerhouses.
And we really have to shift our entire mental framework for this.
How so?
Well, if your mental image of a server is just like a beefy desktop computer sitting on a wire shelf, we need to completely discard that.
Right. Forget the wire shelf.
Exactly. What we are looking at today are massive, highly integrated, liquid-cooled superorganisms.
Superorganisms. I like that.
Yeah, and understanding how these systems are managed by software, how they are physically stacked in 3 dimensions, and how they are cooled is absolutely crucial for grasping the true scale of modern compute power.
Okay, let's unpack this. To do that, we actually have an incredible stack of source material right here on the desk.
We really do. It's a great collection.
We are looking at a highly technical configuration document detailing SCC management protocols, which is essentially the central nervous system for all of this hardware.
Right, the brain of the operation.
Exactly. And then we have these incredibly detailed architectural diagrams directly from Supermicro.
Those blueprints are fascinating.
They really are. They show us exactly what goes into their standard liquid-cooled racks, and it all culminates in a full microscopic anatomical breakdown of the massive, almost mythic NVIDIA GB200 rack.
It is a phenomenal set of documents to put side by side, because usually, you only see the software side or the hardware side in isolation.
Right, they're kept separate.
Yeah. But here, we can actually connect the abstract software management limits directly to the punishing physical realities of power, space, network cables, and like we said, raw heat.
Okay, so before we can look at the shiny heavy metal, and before we talk about liquid cooling and raw processing power, we have to understand the invisible conductor that makes the entire orchestra play.
The management layer.
Right. We need to talk about SCC management.
That is definitely the logical place to begin. So SCC stands for Server Cluster Control, or in this specific hardware ecosystem, Supermicro Cluster Control.
Got it.
Think of it as the overarching management software layer. I mean, when you have hundreds or thousands of servers, you can't have humans manually logging into them individually with the keyboard and monitor.
Right. You can't just walk down the aisle checking screens.
Exactly. You can't just walk up to check if a single fan is spinning, or if a processor is throttling due to heat, or if a hard drive is about to fail.
It would take an army of people.
It would. So you need a centralized, automated management system that aggregates all that telemetry data. But, and this is the crucial part, that management software itself runs on physical computers.
Which means it has its own physical and computational limits.
Precisely.
And the numbers in our source document lay out those limits in black and white. It basically divides the management world into 2 distinct categories, non-HA and HA.
Right.
So let's start with non-HA, which stands for non-high availability. The document states that in a non-HA setup, a single virtual machine can manage 15 racks.
Yes, 15 standard racks.
But let's pause for a second because we throw the term VM around a lot. To make sure everyone is on the same page, a virtual machine isn't some, abstract ghost floating in the cloud.
No, far from it. A virtual machine is a very specific slice of physical reality.
How would you visualize it for the listener?
Well, imagine a massive physical server as an empty apartment building.
Okay, an empty building.
The virtualization software comes in and builds walls, creating individual apartments. Each of those apartments is a virtual machine.
Oh, that makes sense.
It has its own dedicated chunk of the physical processor, its own dedicated slice of the physical RAM, and its own operating system.
So it thinks it's a completely independent computer.
Right. It thinks it is completely independent, but it is just securely sharing the underlying hardware with the other VMs in the building.
So in this non-HA setup, you dedicate one of those apartments, one virtual machine, and its sole job in life is to act as the overarching brain, basically monitoring the hardware across 15 massive physical racks.
Exactly.
But obviously, modern data centers are vastly bigger than 15 racks.
Oh, yeah. Usually hundreds of racks.
Right. So the document says that to expand your management footprint, you add what they call a worker node.
Right. You scale out.
And adding one worker node adds management capacity for exactly 30 more racks.
That's a huge jump.
It is. And then at the bottom of that column, there is an absolute hard maximum limit listed. 165 racks.
Yeah, for standard enterprise and high-performance computing racks, 165 is the absolute ceiling for this specific management architecture.
You can't just keep adding worker nodes forever.
No, you really can't.
So let's actually do the math on this, because I think it really helps visualize the scale and the modularity of the system.
Let's do it.
Okay, let's say you are the IT director. You start with your base software, the single VM, which covers your first 15 racks.
Right, your baseline.
But your company is growing, and you want to push this architecture to its absolute maximum of 165 racks.
Okay.
Let's see. 165 total racks minus the original 15 leaves you with 150 racks of capacity that you still need to actively manage.
So you have a gap of 150 racks.
Exactly.
And you need to bridge that gap using the modular worker nodes.
Right. And since the source explicitly states that every single worker node handles exactly 30 racks, it's just straightforward division.
Right. 150 divided by 30.
Which is exactly 5. So to push a non-HA system to its architectural limit, you have your primary single VM plus exactly 5 worker nodes. That is your complete management roster.
It's a very precise, predictable scaling mechanism,
Mm-hmm.
which, accountants and network architects absolutely love.
I bet they do.
However, in a major enterprise-grade data center, you would almost never want to actually run a non-HA setup.
Why not?
Because non-high availability is really just a polite way of saying single point of failure.
Ah, yeah, that sounds bad.
It is. If the physical server that happens to be hosting that one primary virtual machine loses power, or if the VM's operating system crashes, it happens all the time. Your entire management view of those 165 racks goes instantly dark.
Wow. Even if the racks themselves are fine.
Exactly. The servers might still be doing their jobs, crunching numbers or serving websites, but you as the administrator are flying totally blind.
So you wouldn't know if a fire broke out in rack 42.
You'd have no idea. Which is terrifying when you're dealing with tens of millions of dollars of hardware.
So that brings us to the second category in the document, HA, or high availability.
Right, the enterprise standard.
The source tells us that an HA setup starts with 3 master VMs, and those 3 master VMs together manage a baseline of 75 racks.
And this introduces a really beautiful piece of engineering logic called a distributed quorum.
A distributed quorum?
Yeah. Instead of one single point of failure, you have 3 master VMs that are constantly talking to each other, syncing their databases in real time, and acting as a unified cluster.
So they share the load.
They do. And if one master VM suddenly dies, the other 2 realize it within milliseconds and seamlessly take over the full load.
Okay, but wait. Why 3, though? Why not just have 2 master VMs? A primary and a backup seems like the logical, cost-effective way to build redundancy.
That's a great question, but it actually leads to one of the most dangerous situations in computer science. It's known as the split brain scenario.
It's a lip brain.
Yeah. Imagine if you only have 2 master VMs and the network cable connecting them gets severed.
Okay, so they can't talk.
Right? Both of them are still awake, but they can't see each other. Master A thinks Master B is dead, so it tries to take full control of the data center.
Oh, no.
And Master B thinks Master A is dead, so it also tries to take control.
So they both think they are the lone survivor.
Exactly. They start sending conflicting commands, rewriting each other's databases, and essentially tearing the network apart from the inside.
That sounds like a total nightmare.
It is. But if you have three master VMs, you have a built-in tiebreaker mechanism, a quorum.
Ah, I see.
If the network splinters, the two VMs that can still talk to each other realize they hold a majority 2 out of 3.
Right.
They form a quorum, take control, and intentionally ignore the isolated third VM until the network is physically fixed. It mathematically prevents the split brain scenario.
That is brilliant. It essentially uses democracy to prevent a digital civil war.
That's a perfect way to describe it.
But let's look at the efficiency difference between the two setups, though. Because in the non-HA system, one VM manages 15 racks. But in the HA system, 3 master VMs manage a baseline of 75 racks.
Yeah, the math changes.
If we just divide 75 by 3, that averages out to 25 racks per master VM. That is a massive jump in efficiency. How is the HA cluster managing 25 racks per virtual machine when the Solar system could only handle 15?
Well, it really comes down to the mechanics of cluster databases and distributed systems.
How so?
When you have a single VM, it has to do every single chore itself. It handles the database writes, it renders the user interface for the administrators, it processes the API calls, and it listens to all the inbound telemetry from the racks.
So it's just constantly multitasking.
Exactly. It is constantly context switching, which is inefficient. But when you cluster 3 master VMs together, they distribute those specialized tasks.
Ah, division of labor.
Yes, they can balance the inbound network traffic. While one VM is busy writing heavy logs to the database, the other 2 are handling the UI and the real-time alerts. That division of labor allows the cluster as a whole to handle a significantly higher baseline.
That makes total sense. And the scaling works exactly the same way from there.
Right.
The document shows that even in the HA setup, adding one worker node still adds exactly 30 racks of capacity.
The worker node capacity doesn't change.
And it still hits that exact same hard ceiling, 165 racks maximum.
So to get from the HA baseline of 75 racks up to the 165 maximum, you need 90 more racks of capacity.
Okay.
And 90 divided by 30 racks per worker node means you deploy exactly 3 worker nodes.
Got it.
So your maxed out AK management cluster is 3 master VMs and 3 worker nodes overseeing 165 racks.
You know, I was trying to visualize the hierarchy of this software earlier, and I came up with an analogy.
Oh, let's hear it.
Okay, think of this whole SCC management system like managing a massive, sprawling network of fast food restaurants.
Okay, I'm with you.
A non-HA system is like having one single general manager that single VM overseeing 15 locations. If that manager gets sick or their car breaks down, the entire oversight system halts.
Right. Nobody at corporate knows what the inventory looks like.
Exactly. It's a perfect recipe for operational collapse.
Definitely.
Now, the HA system high availability is like hiring a team of 3 elite regional managers. These are your 3 master VMs.
I like this.
They're perfectly synced, constantly on group chat with each other, sharing the load of 75 restaurant locations.
And if one gets stuck in traffic,
The other 2 just absorb their route. The operation never skips a beat because there's always a quorum.
the analogy holds up really well. And what about the worker nodes?
Well, the worker nodes are the assistant managers. When your restaurant chain explodes in popularity and you need to open more locations, you don't burden your elite regional managers with the day-to-day trivialities of the new spots.
No, they're too busy.
Right. You parachute in an assistant manager, a worker node, and their only job is to handle the mundane telemetry of exactly 30 new locations.
Okay.
They count the spatulas, they check the fryer temperatures, and then they report a clean, condensed summary back up to the regional managers.
That maps beautifully to the network topology, actually. The worker nodes aggregate the heavy, noisy, raw data from the server racks, filter it, and only pass the critical alerts and compressed summaries up to the master VMs.
Which prevents the core database from being overwhelmed.
Exactly.
But that brings up the big mystery of this document.
The hard limit.
Yes. In both the non-HA and the HA setups, the text is incredibly firm on this. Greater than 165 racks requires customization.
Yes, it hits a wall.
Why 165? I mean, what physically or mathematically happens at rack 166 that breaks the system so fundamentally that you can't just throw another worker node at it?
It's a great question. The 165 rack hard limit really points to a built-in threshold for standard network bandwidth and database physics.
Database physics.
Yeah. Think about what a single modern server rack actually is. It's not just sending a slow ping every few minutes saying, oh, I'm still here.
Right. It's doing a lot more than that.
A single rack contains dozens of independent servers. Each of those servers has its own motherboard, which has dozens of microscopic temperature sensors, voltage regulators, fan speed monitors, and memory error logs.
That's a lot of sensors.
Every single piece of hardware is constantly screaming data into the network multiple times a second.
So it sounds like a sheer volume issue, a data tsunami.
A total network storm. Beyond 165 racks, the sheer volume of that telemetry, we are talking tens of millions of tiny data points being generated every single second, creates a bottleneck at the database level.
Wow. Tens of millions per second.
Yeah. The standard out-of-the-box relational database architecture that Supermicro uses for SCC simply cannot ingest, index, and query that much unstructured data in real time without severe lag.
It just chokes on it.
It does. If you go beyond 165, you'll likely need a completely bespoke, highly distributed architectural approach.
Like what?
Well, you are moving out of standard management software and into the realm of custom message brokers like Apache Kafka and separate massive time series databases just to handle the noise.
That makes perfect sense. 165 is basically the limit of standard off-the-shelf management physics.
Exactly.
But as I was reading further down the source document, I hit a glaring discrepancy.
Oh, the NVIDIA racks.
Yes, everything we just talked about applies to what the document calls Type 1, Type 2, and Type 3 racks, AI, Enterprise, and HPC standard racks.
Right.
But then there is a separate section entirely dedicated to Type 4, the NVIDIA rack. Specifically, the document calls it the GB200 PowerShelf plus CDU rack.
The absolute apex predator of the data center.
The management limits for this specific NVIDIA rack completely break all the rules we just learned.
They really do.
Let me read these numbers because they are strange. For a non-HA setup on the NVIDIA racks, it doesn't start at 15 racks, it starts at only 10.
A drop right off the bat.
And adding a worker node doesn't give you 30 racks of capacity, it only gives you 20.
Right.
And the absolute maximum drops from 165 all the way down to 110.
And that penalty applies to the HA configuration as well.
It does. HA for NVIDIA racks starts at 50 instead of 75. Workers still only add 20. And the maximum ceiling is severely capped at 110 racks.
It's a massive reduction.
Why is the NVIDIA rack being penalized so heavily by the very software designed to run it?
What's fascinating here is that this software limitation is actually our first major clue about the physical structural density of the hardware.
How so?
The software isn't broken, it's exhausted.
Exhausted.
Yeah. Based strictly on the text in our source, these Type 4 racks explicitly contain power shelves and CDUs, which stands for coolant distribution units.
Oh, right. The liquid cooling engines we mentioned at the start.
Yes. We can deduce that the internal complexity of a single NVIDIA GB200 rack is vastly superior to a standard enterprise rack.
So there's just more going on inside it.
Much more. The SCC software is no longer just pinging standard computer motherboards.
Yeah?
It now has to actively manage industrial-grade fluid dynamics.
Wow, fluid dynamics.
It has to monitor flow rates, coolant temperatures, pump pressures, and massive specialized power distribution hardware built right into the metal of the rack itself.
So the telemetry footprint of one NVIDIA rack is just incredibly bloated.
Vastly bloated. It demands significantly more management bandwidth, more IP addresses, and vastly more constant polling per rack just to ensure it doesn't melt.
So it's just louder on the network.
Exactly. The management system hits its database limits faster because every individual NVIDIA rack is generating the telemetry noise of 2 or 3 standard racks.
Okay, so we've established that the software taps out at 110 racks for NVIDIA because it's practically deafened by the screaming telemetry data.
Yes.
The data doesn't just generate itself out of thin air. It's a byproduct of intense calculation, heat, and physical friction.
Right, it comes from the metal.
So let's look at the physical architecture creating that heat to understand why the software is drowning. That brings us to our next set of blueprints. The physical 48U rack layouts from Supermicro.
For anyone trying to visualize this at home, we probably need to define U.
Yes. Oh, right. Good point.
It stands for rack unit. It is the global standard unit of measurement for the height of electronic equipment mounted in a standard 19-inch wide server rack.
Okay.
1U is exactly 1.75 inches high.
Got it.
So a 48U rack is a massive metal cabinet roughly 7 feet tall. When you walk down the aisle of a hyperscale data center, these 48U racks are the skyscrapers towering over you.
And the source material lays out three distinct pillars or types of architectures that fill these 7-foot skyscrapers.
Let's walk through them.
Okay, starting with type 1, the ALM rack. The blueprint describes this as GPU-optimized architecture. It holds up to 64 of the latest GPUs across 8 GPU servers.
That's incredibly dense.
Specifically, the inventory lists 8 4U servers packed with NVIDIA HGX B200s. And to keep it from melting, the inventory lists 1 CDU and 2 vertical CDMs.
The density there is specifically engineered for one task training large language models.
Those like the AI we talk to every day.
Yeah, exactly. And when the blueprint says 4U8 GPU server, it means every single one of those 8 servers takes up 4 units of height, about 7 inches tall, and holds 8 massive graphic processing units inside it.
Let's hold that thought on the AI rack's cooling, because I want to contrast it with the next one.
Okay, sure.
Next is Type 2, the enterprise rack. The blueprint calls this industry-leading multi-node architecture. And the numbers change drastically here.
Very different setup.
Instead of 8 massive servers, it holds up to 76 server nodes, or 19 systems. Specifically, it uses 19 big twin servers, which are labeled 2U4N.
Yeah.
It has 1 CDU, 1 vertical CDM, and 1 switch.
So let's decipher that 2U4N code for a second.
Yeah, what does that mean?
It means each metal chassis takes up 2 rack units of height, but contains 4 separate independent compute nodes inside it.
Okay, 4 nodes in one chassis.
Right, hence the brand name twin, or in this case, a quad node twin. So 19 of those chassis multiply out to 76 total independent servers in one 7-foot rack.
What is the physical advantage of putting 4 nodes in one chassis? Why not just have 76 separate tiny 1U servers?
Mostly efficiency and shared resources. By putting 4 compute nodes in one 2U chassis, they can share massive, highly efficient power supplies and large cooling fans.
Oh, instead of duplicating them.
Right. If you had 76 individual servers, you'd need 76 separate power supplies, which is just a total nightmare for wiring and power loss.
That makes sense.
This setup tells us that the enterprise rack prioritizes flexibility, redundancy, and balance. It's designed to run the bread and butter of the corporate world.
Like what?
HR databases, thousands of virtual employee desktops, email servers, web applications. It needs balanced input-output and memory rather than the raw, brute force floating point math required for AI.
Okay, that brings us to Type 3, the high-density HPC rack. HPC meaning high-performance computing.
Right.
The blueprint labels this a purpose-built HPC at scale solution. This one pushes the node count even further than the enterprise rack.
The densest one yet.
Yeah, up to 84 server nodes or 21 systems. It uses 21 Flex Twin 2U4N servers. And just like the enterprise rack, it lists 1 CDU, 1 vertical CDM, and 1 switch.
So the high-performance computing rack represents the absolute maximum independent node density shown in these diagrams. 84 distinct servers in one cabinet.
That's a lot of computers in one box.
It is. This is built for massive parallel processing. We are talking about academic or scientific workloads, granular global weather forecasting, complex genomic sequencing, or massive financial risk modeling for Wall Street.
Right, heavy number crunching.
Exactly. Where the AI rack uses massive, power-hungry GPUs, the HTC rack typically relies on a vast army of highly efficient CPUs working in perfect unison on a single massive data set.
Okay, so we have these 3 distinct pillars, AI, enterprise, and HPC.
Yes.
But as I was reading the physical inventory of this 48U space, the math on the AI rack really jumped out at me.
Oh. What caught your eye?
Well, if you look at the enterprise and HPC racks, they both need exactly 1 vertical CDM for cooling, and they both include a networking switch right there in the inventory list. Standard, expected data center stuff.
Right, a switch to connect to the network.
But the ALM rack, it requires 2.0 vertical CDMs, and it completely drops the switch from its inventory.
Yeah, it completely gets rid of it.
Why does the AI rack need double the liquid cooling plumbing, and how on earth is it communicating with the rest of the building if there is no switch in the rack?
That cuts right to the heart of what makes AI infrastructure so violently different from standard computing.
Okay, let's hear it.
Let's do the physical math on that 48-unit space. In the ALM rack, you have 8 servers, and each server takes up 4U of vertical space. 8 times 4 is 32U.
Right.
That means out of a 48U rack, 32 units are dedicated purely to compute.
Which leaves only 16U of empty physical space in the entire metal cabinet.
Exactly. Now, consider what is inside that 32U of compute 64 NVIDIA HGX B200 GPUs.
That sounds hot.
Very hot. Those specific chips draw an astronomical amount of electrical power. And the laws of thermodynamics dictate that almost 100% of the electrical power consumed by a processor is instantly converted into heat.
So it's basically a giant heater?
It is. The sheer thermal density of 64 B200 GPUs operating at maximum load is so extreme that a single vertical CDM, a coolant distribution manifold, which is the main pipe delivering the liquid, simply cannot push fluid fast enough to capture the heat before the chips melt.
So they literally have to double the physical plumbing.
They double the plumbing. They run two massive vertical CDMs up the sides of the rack to ensure an adequate high-pressure liquid flow rate to every single GPU block.
Wow.
The cooling infrastructure demands are so physically large that they just cannibalize the space and power that would normally go to networking gear.
Which explains the missing switch in the inventory.
It does. But it also points to a fundamental shift in networking philosophy entirely. Well, the absence of the top-of-rack switch in the AI inventory list suggests that for these massive GPU clusters, networking is handled entirely differently.
Differently than standard racks.
Right. In an enterprise or HPC rack, you have a standard top-of-rack switch, literally a networking box at the very top of the cabinet that all 76 or 84 servers plug into.
Okay.
That switch then acts as a choke point, routing traffic up to the wider data center and back down.
And a choke point is fine for sending an email or querying an HR database?
Exactly. But in a dedicated AI training cluster, the GPUs need to talk to GPUs in other racks with almost zero latency to synchronize their math.
I see where this is going.
If you force all that massive GPU data up into a single top-of-rack switch and then down another cable, you create a catastrophic traffic jam.
So putting a standard switch in the rack would just starve the GPUs of data.
It would ruin the entire multi-million-dollar investment. Instead, modern AI data centers use external, highly specialized spine and leaf networking architectures.
Spine and leaf.
Yeah. Picture a standard network like a tree branches all connect to a single trunk. That's your choke point.
Right.
A spine and leaf topology is more like a highly structured grid or mesh. Every leaf switch is directly connected to every spine switch.
So there are multiple paths.
Exactly. This structural geometry means that no matter which rack a GPU is in, it is always the exact same number of microscopic hops away from any other GPU in the building. It physically prevents traffic jams.
That is incredible.
But this networking gear is so vast and power-hungry, it requires its own dedicated racks elsewhere on the floor. It literally cannot fit in the AI compute rack.
That is just fascinating. So 64 GPUs in the Type 1 AI rack pushes the thermal and networking limits of a 7-foot space to the absolute brink. They have to double the pipes and evict the networking just to make it fit.
They do.
But then I turn the page to the final diagram in our sources, and the blueprint reveals an entirely different beast altogether.
The GB200.
Yes. We are moving from comparing standard rack types to microscopically examining a single ultimate architectural marvel, the dedicated NVIDIA GB200 rack.
This is where standard engineering definitions really start to break down.
Why is that?
Because the GB200 rack is not a collection of individual servers stacked in a metal box. It is a meticulously engineered, unified supercomputer contained within a single monolithic cabinet.
Well, let's dissect the anatomy of this behemoth, top to bottom, exactly as the diagram lays it out.
Sounds good.
At the very top, we have the management networking section. This contains an in-band management switch and an out-of-band management switch. Let's define the difference there because it's a crucial fail-safe.
Right. In-band management is the primary highway. It's how the operating systems, the applications, and the day-to-day data traffic move.
Okay, the normal route.
Exactly. But out-of-band management is the secure, physical backdoor service corridor.
Like the red telephone in the bunker.
That's a great way to think of it. Even if the entire compute system crashes, the operating system hangs, and the in-band network is totally dead.
A total freeze.
The out-of-band switch has its own dedicated low-level power and a completely separate physical network connection.
So it's still alive?
It is. It allows a technician sitting in a different country to remotely log in, diagnose the physical hardware at the motherboard level, and force a reboot. It's the ultimate physical failsafe for when the software goes rogue.
That's a huge relief to have. And right below those fail-safe switches, we hit the heavy calculation engines. The blueprint calls this the upper compute section.
Here we go.
It is made up of 10 compute trays. And the contents of each tray are just staggering. Every single one of those 10 trays holds 4 NVIDIA Blackwell GPUs and 2 NVIDIA Grace CPUs.
The Blackwell architecture is currently the pinnacle of AI calculation.
Right.
But what is truly revolutionary here is pairing it directly with the Grace CPU on the exact same tray.
Why is that so revolutionary? Don't computers always have both?
They do. But historically, GPUs and CPUs sit on opposite sides of a motherboard and communicate over a standard PCIe bus, which acts like a slow toll bridge.
Ah, another bottleneck.
Exactly. By fusing them together on the same physical board in the GB200 tray, they can share memory instantly. The CPU doesn't have to wait for data to travel across a motherboard. It has direct, unimpeded access to the GPU's brain.
That's a huge leap in efficiency.
It is.
Then, below the upper compute section, sitting right in the very geometric center of the rack, is the compute interconnect.
The heart of the machine.
This section holds 9 NVLink switches. And the diagram states these switches connect a total of 72 GPUs and 36 CPUs at a staggering speed of 1.8 terabytes per second.
We will definitely come back to that 1.8 terabytes number because it is arguably the most important metric in the entire document.
Oh, absolutely. But let's finish the physical layout first.
Right, continuing down.
Below the middle switches, we have the lower compute section. This looks just like the top, but slightly smaller. It has 8 compute trays. And again, each tray holds 4 Blackwell GPUs and 2 Grace CPUs. And finally, at the very bottom of the rack, we have the liquid cooling options, which takes up a significant amount of the remaining vertical space.
The physical layout here is incredibly deliberate. I mean, nothing is placed randomly for aesthetic reasons. It is entirely dictated by physics.
Here's where it gets really interesting. I was looking at this diagram, and I wanted to see if the math actually checked out.
Oh, nice.
Yeah, I wanted to prove the engineering precision of this blueprint live. So let's calculate the exact component count based on the individual tray.
I love a live math check. Let's walk through it.
Okay, starting with the upper compute section, we have 10 trays. Each tray has 4 GPUs. So 10 times 4 is 40 GPUs in the top half.
Right, 40 up top.
And for the processors, 10 trays times 2 CPUs each. That is 20 CPUs in the top half.
Okay, 40 GPUs, 20 CPUs up top.
Now for the lower compute section, we have 8 trays down there. 8 trays times 4 GPUs each is 32 GPUs.
Yep.
And 8 trays times 2 CPUs each is 16 CPUs in the bottom half.
Now aggregate it all.
Right, so top GPUs plus bottom GPUs, 40 plus 32 equals exactly 72 GPUs.
Perfect.
And top CPUs plus bottom CPUs, 20 plus 16 equals exactly 36 CPUs.
72 and 36.
72 GPUs and 36 CPUs in total. And what did the blueprint say the 9 NVLink switches in the middle were connecting? Exactly 72 GPUs and 36 CPUs.
It matches perfectly.
It is a perfect closed-loop architectural match. There is no wasted space, no orphaned components, no extra capacity left on the table. Every single chip is accounted for and hardwired into that central switch cluster.
That perfectly validated math isn't just satisfying to calculate, it reveals the uncompromising design philosophy of the system. Let's talk about a physical geometry. Where are those 9 NVLink switches located?
In the middle.
Right. They are physically placed in the exact middle of the cabinet. Why?
Because it makes them equidistant to the top 10 trays and the bottom 8 trays.
It is entirely about distance. If we connect this to the bigger picture, in the world of high-performance AI calculation, physical distance equals latency.
Right. The time it takes for a signal to travel.
Exactly. Data moving through copper cables or even fiber optic cables takes time, even at a fraction of the speed of light. If those NVLink switches were placed at the very top of the rack, the data traveling from the bottom 8 trays would have to travel several feet further than the data from the top trays.
Which creates a microscopic delay.
A delay of a few nanoseconds, sure.
Does a few nanoseconds really matter?
Yes. In synchronous AI training, where 72 GPUs must calculate and update their weights at the exact same clock cycle, a few nanoseconds of delay means the faster GPUs sit idle waiting for the slower ones.
Oh, wow.
It destroys the efficiency. By placing the 9 NVLink switches in the exact geometric center, Supermicro and NVIDIA minimize the physical cable length to both the upper and lower sections. They are fighting for nanoseconds using physical 3-dimensional geometry.
That is incredible. They're literally routing cables to beat the speed of light limitations.
They are.
And that brings us back to that mind-bending speed listed in the diagram. The NVLink switches interconnect all 72 GPUs and 36 CPUs at 1.8 terabytes per second. Terabytes.
To contextualize 1.8 terabytes per second, we really need a massive physical metaphor.
I was actually trying to picture this earlier. Think about streaming Netflix.
Okay.
A high-definition movie stream is like a few megabytes a second.
Yeah.
To equal 1.8 terabytes, imagine taking every single pixel of every movie currently streaming on Netflix to every user globally at this exact moment.
That is an immense amount of data.
Now, imagine taking all of that global visual data and forcing it through a physical pipe the width of a pencil every single second.
Wow.
That is the volume of data moving inside this one metal cabinet.
That visual perfectly captures the violence of the data transfer. And remember, that is not the speed to the outside world, that is the speed at which the internal components are talking to each other.
If they are moving data at 1.8 terabytes a second inside the rack, the management software or the operating system can't possibly be tracking 72 individual GPUs anymore, right?
Oh, way.
The latency of checking in, asking permission to send data, and verifying receipts would ruin the speed. Does the software just see this whole tower as one giant chip?
You have hit the exact core of the paradigm shift. From an algorithmic and software standpoint, those 72 individual Blackwell GPUs are effectively fused together.
Fused together.
Yeah, because the NVLink interconnect is so phenomenally fast, the latency that usually separates individual computers is completely erased. The software does not see 72 distinct graphics cards. It sees one giant unified monolithic brain with 72 lobes.
That totally explains why the SCC management software tops out so quickly with these racks.
Precisely. You cannot train the next generation of artificial intelligence by asking 72 separate computers to work together over standard Ethernet cables.
They just wait on each other.
Right, they would spend 90% of their time waiting. You have to fuse them into a single entity.
A single 72-lobed brain. But here is the massive elephant in the room.
The heat.
The heat. You pack 72 Blackwell GPUs, which are some of the most power-hungry, dense chips ever manufactured, and 36 Grace CPUs into one single sealed physical tower. The thermal challenge there is completely unprecedented.
It really is.
I mean, the sheer amount of electrical current flowing into that cabinet. How does this thing not instantly catch fire the moment a technician presses the power button?
It is a valid, literal question. The heat generated by that density of silicon is enough to physically melt standard server components, solder, and plastic in a matter of minutes if the cooling fails.
Minutes?
Yes. Air cooling, using fans to blow chilled air over metal heat sinks, is completely obsolete at this level. You literally cannot move enough air fast enough.
You have to use liquid.
You must use liquid, because liquid has a drastically higher specific heat capacity than air. It absorbs and carries away heat vastly more efficiently.
Which bridges us directly to the bottom section of the GB200 rack diagram, the liquid cooling options.
Right, let's look at those.
The blueprint lays out two distinct cooling options for this monster. Let's look at option 1. It details a Supermicro 250 kilowatt capacity coolant distribution unit, or CDU, equipped with a redundant PSU and dual hot swap pumps.
The numbers there are staggering to anyone who has run a data center. 250 kilowatts of cooling capacity required for a single rack.
Let me unpack some of that terminology for the listener because it's a dense engineering sentence. First, redundant PSU means backup power supply units.
Correct.
If the primary electrical supply driving the cooling system fails, a backup instantly takes over. Because, as we said, if the cooling stops for even 10 seconds, the rack cooks itself into slag.
Fail-safes upon fail-safes. The margin for error is absolute zero.
And dual hot swap pumps is even more fascinating to me. It means there are two massive water pumps constantly circulating the coolant fluid.
Right.
If one of those physical pumps burns out or starts grinding its bearings while the system is in the middle of calculating a billion-dollar AI model, the system doesn't shut down.
No, it keeps going.
A technician can literally walk up to the rack, unlatch the broken pump, pull it completely out of the machine, and slide a brand new one in, all while the massive supercomputer above it is running at full power. That physical maneuver is what hot swapping means.
It is the absolute pinnacle of engineering for uptime. You never, ever want to stop the calculation, because restarting a massive AI training run can cost hundreds of thousands of dollars in wasted time and electricity.
Wow.
But this 250 kilowatt requirement raises a massive issue regarding physical building infrastructure.
Like the building itself can't handle it.
Exactly. Historically, an entire standard enterprise rack full of servers might draw 10, maybe 15 kilowatts of power total. This single GB200 rack requires 250 kilowatts of cooling capacity alone.
So the building itself really has to change.
The data center has to be structurally plumbed like a chemical plant.
Plumbed like a chemical plant, that's a vivid image.
It's true. You need massive, facility-level industrial water pipes running under the floor tiles to deliver thousands of gallons of chilled water to the rack's CDU, and massive return pipes to carry the near-boiling water away to external cooling towers on the roof.
But what if you don't have a data center built like a chemical plant? What if you are, say, a research university or a mid-sized tech company with a slightly older data center, but you desperately need the AI training power of the GP200 to stay competitive?
That is the big problem.
That is where option 2 on the blueprint comes in. The diagram lists a 240 kilowatt and a 180 kilowatt capacity liquid-to-air solution. And right next to it, in parentheses, is the most crucial caveat in the entire document: no facility water required.
That parenthetical note is a massive business strategy wrapped in an engineering specification.
A business strategy.
Yeah, no facility water required. This is Supermicro's solution for the global infrastructure bottleneck. They know there aren't enough liquid-plumb data centers in the world to meet the demand for Blackwell GPUs.
How does that actually work mechanically, though? If it's a liquid-cooled rack, how does it not need facility water?
Okay, so in option 1, the rack's internal liquid loop exchanges its heat with the building's massive external water loop. But in option 2, the liquid-to-air solution, the rack is completely self-contained. It operates like a closed loop.
Like a self-contained ecosystem.
Exactly. The internal coolant fluid circulates over the 72 GPUs, absorbs the extreme heat, and then pumps down to a massive radiator located at the bottom of the rack.
Oh, like the radiator in the front of a car?
Precisely like a car radiator.
Yeah.
Then, incredibly powerful industrial fans blast the ambient air of the data center straight through that radiator.
Wait!
The heat transfers from the liquid into the air, and that scorching hot air is blasted out the back of the rack into the room.
Wait, hold on. I need to push back on this.
Sure.
If you are blasting up to 250 kilowatts of raw heat into a room that isn't plumbed for liquid cooling, aren't you just turning the data center into a pizza oven?
You absolutely are.
How can standard CRA units, the computer room air conditioning units on the walls, possibly keep up with that volume of heat without melting the older enterprise servers sitting in the rack right next door?
You are identifying the exact physical crisis this creates. It is a massive Band-Aid solution.
Sounds like it.
To survive this, data centers have to implement extreme thermal aisles. They physically enclose the backs of these racks into sealed corridors called hot aisles.
Oh, to trap the heat.
Exactly. Capturing that scorching air and forcing it directly up into the ceiling plenums where the massive AC units try to suck it away.
That sounds intense.
But you are absolutely right. It pushes traditional air conditioning to the absolute brink of failure. It's a brute force method to get AI compute into older buildings, but it is thermally terrifying.
Let's really think about what that means for the room itself to put that heat into perspective. I want you to connect with this, listener.
Yes, this is a great exercise.
Think about the physical space you are sitting in right now as you listen to this. Maybe it's a home office, maybe it's your living room, maybe the cabin of your car.
Just look around the room.
Now, I want you to recall our hook from the beginning of the deep dive. The heat of 2,500 old-school 100-watt incandescent light bulbs.
The ones that will blister your skin if you try to unscrew them while they are on.
Yes, 2,500 of them, all turned on simultaneously, glowing and radiating heat. Now, take all of those bulbs and pack them tightly into a physical space roughly the size of your kitchen refrigerator.
It creates a thermal density that the human brain really struggles to actually visualize.
It does. That is the inferno that a 250 kilowatt CDU is actively managing and suppressing every single second of every single day.
Without a single pause.
And if you use the liquid-to-air option 2, that refrigerator is blasting the heat of 2,500 light bulbs directly out its back door into the room you're standing in.
The sheer invisible violence of the physics happening silently inside these black metal cabinets is just mind-blowing.
It truly is. We look at these sleek black towers with their flashing blue and green lights, and they look so quiet and clinical.
Right, very sterile.
But inside it is a raging storm of thermodynamics, fluid mechanics, and electrical current, all perfectly balanced on a knife's edge just to teach a machine how to process human language.
It's an incredible feat of engineering.
Wow. Okay, we have covered an immense amount of ground today.
We really have.
We started at the invisible software layer, exploring the mathematical limits of SCC management. We saw how standard architectures cap out at 165 racks before causing a network storm.
Right, database physics.
Exactly. But then we saw how the immense telemetry footprint of ultra-dense NVIDIA systems forces that management limit down to just 110 racks.
Because it's practically deafened by the noise.
Yes. We also unpacked the physical architectural differences within the standard 48U space.
Contrasting the different pillars.
Right. We contrasted the 32U compute density of the AI rack and why it has to evict its own networking gear for double the plumbing, with the massive 84-node scaling of the high-performance computing Flex Twins designed for parallel processing.
And finally, we practically took a microscope to the ultimate super rack, the GB200.
The behemoth itself.
We counted the 72 Blackwell GPUs. We explored the nanosecond geometry of the 1.8 terabyte per second NVLink brainstem in the middle, and we stared into the 250 kilowatt liquid-cooled furnace at the bottom.
It's been a wild ride.
But, as we summarize this incredible journey through these blueprints, there is a fundamental tension that emerges.
Oh, what kind of tension?
Well, we've seen that through miraculous, uncompromising engineering, we can currently fit 72 Blackwell GPUs into a single tower, supported by a massive 250 kilowatt liquid cooling unit.
Right, we've pushed the limits.
But as we look at the limitations of the SCC management software, which is already dropping from a 165 rack capacity down to just 110 for these dense systems, because it is deafened by the noise we have, to ask a difficult question about the future.
What's that?
Are we rapidly approaching the hard physical limits of what humanity can pack into a single 48-unit physical space?
Oh, wow.
I mean, we are already doubling the plumbing and removing the network switches just to make room.
It's bursting at the seams.
Exactly. When 250 kilowatt liquid cooling inevitably maxes out and water physically can no longer absorb the heat fast enough, what radically new, perhaps entirely alien architecture will the next generation of AI demand to keep growing?
That is terrifying.
Will we abandon the 48U rack entirely? Will we submerge the entire data center in fluid?
That is a staggering thought to leave on, because the blueprints we looked at today, as alien, dense, and incomprehensibly complex as they seem to us right now, they might just be the simple human-scale sketches of what is yet to come.
We're just at the beginning.
The muddy waters of the future are deep, and they are heating up fast. Thank you so much for joining us on this deep dive into the absolute limits of physical computing architecture. Keep questioning, keep looking closely at the diagrams, and as always, stay curious.